bon matin, bienvenue à tous. So I'm going to do the introduction in English. So we're very happy to have Professor Andrew Musser here for a seminar. I found your bio on your group website, so I'm just going to read the first two sentences, which I love. So Andrew originally trained as a physicist with an eye towards solving complex global problems. Not infrequently accused of being a spy, he spent 2 years working and studying in Russia. And he tried his hand at organic synthesis and genetic engineering at the Manchester Interdisciplinary Biocenter in the UK. And there's more to the spy story that he can tell you about offline. So after his bachelor's, Andrew did his master's in the Netherlands, followed by a PhD at Cambridge in the group of Richard Friend, where he did ultrafast spectroscopy and studied singlet fission. That was followed by a postdoc in Cambridge, as well as a postdoc with David Lindsay at Sheffield. Since 2019, Andrew has been a professor at Cornell University in the Department of Chemistry and Chemical Biology, correct? And he's been working both on singlet fission, so he's done pioneering work on understanding spin physics in organic molecules, as well as the microcavities and the strong exciton-photon coupling that give rise to exciton-polaritons. And I believe we'll be hearing about both today. So, Andrew, thank you, and the mic is yours.
All right. Thanks a lot, Stefan. I'm really happy to have the chance to come up here finally after our belated aborted attempt last year. And I am really happy to, tell you all what my group has been up to in Cornell for the last 6-7 years. But before I do, okay, so how is this going to work? There we go. Before I do, of course, I need to acknowledge the people who actually do all this work. I've put together a really amazing team of graduate students, undergraduates, and postdocs over the years. The people whose work I'm going to present are Rana, a current graduate student who worked as an undergraduate at Kelly, Shohan is a former graduate student who stayed on as a postdoc, another former grad student, David, and 2 postdocs who've gone on to start their own groups. We have a wonderful array of collaborators who provide us interesting materials. We don't do any synthesis in my labs, so we rely on people making very exciting molecules that we can study, or very good theoreticians who can help us better understand our results. And some wonderful funders, however long they last. So I run an ultrafast spectroscopy group at Cornell, and that means that we're interested in really anything that molecules and materials do when they interact with light. Most of our activities fall under 4 distinct areas. So we continue to be very active in singlet fission. This is an exciton multiplication process that could be really powerful to improve the efficiency of the solar cells, has implications for quantum information science. We're working on understanding the fundamental details of this process, how it connects with molecular structure, and see if we can find new ways to make fission happen. We do some fundamental work in spectroscopy, looking at how ultrafast nuclear motion turns out to drive a lot of the processes we're interested in. So we're interested in these vibronic dynamics and whether we can use them as a design principle to actually make organic materials more efficient at what they do. I became a chemist when I joined the department in Cornell, and I thought, well, I should probably think about chemical problems a little bit. And the one that most readily came to mind is how molecules are made in the first place. I have a lot of colleagues who are developing new, more powerful light-activated catalyses to make more challenging molecules. But very often in that part of the field, nobody has any idea what the photon is doing, how these reactions work. So we're working with some of my colleagues to understand the mechanistic details of these new, more powerful photoredox reactions to hopefully design new materials that can do it more efficiently or with the ability to recycle them. But the real heart of my group is the study of exciton-polaritons. This is where about half of my group is active. So this is a manifestation of strong light matter coupling, where there's incredible potential to manipulate potential energy surfaces, change the dynamics of organic materials. But we're really working on the fundamentals still in this area, trying to understand what are these states, what do they really do before we can do anything too fancy with them. But the real idea behind what my group does is that in the end, all roads lead to polaritons. If strong coupling can deliver on its promise, which is a very big if, then it stands to rewrite the potential energy surfaces or the thermodynamics that drive singlet fission, steer new vibronic dynamics on polaritonic potential energy surfaces, and enable new methods of ultra-fast, long-range photoredox catalysis. So everything that we do in our group is kind of with the eye towards seeing, could strong coupling help this or hurt it or modify it in any way? But the background of what we do in my lab, everything is framed by, this thing is really annoying. Do we know how to get rid of it?
You can hide it.
Hide it? Is that going to be more? Hide floating medium. There we go. Okay. Yes, so everything we do in my lab is framed with the concept of organic semiconductors. And this is partially a historical artifact of the fact that I was trained as a physicist, and physicists aren't allowed to work on molecules. So we had to make it semiconductors. We work on pi conjugated materials by and large. And the reason that I got into this in the first place is these have incredible advantages. You can pack materials that look like this into thin films, looking like kind of weird alien devices like this, but they can turn into the same kinds of semiconducting devices as the ones that we're all familiar with in our everyday lives, LEDs, transistors, solar cells. But they have these great advantages. They're produced with bulk scale, often room temperature or low temperature synthesis. You can make vast quantities in a day. They can be processed in the same way that you make a newspaper, if any of the young people in the room still know what those are. And they have this incredible versatility. I could go to a board and, okay, there we go. I could go to a board and draw any number of organic molecules, as long as they follow a few basic rules. And some poor graduate student somewhere will be able to make it. And the odds are it's going to have completely different properties from every molecule that's been made before. Most of the time, they're going to be worse, but sometimes they might be better. And this versatility holds out the promise, then, if we can find the right materials design rules, we can have the perfect molecule, the perfect organic semiconductor to maximize charge carrier transport, or to have very efficient, very fast blue light emission for LEDs, or very broadband absorption and efficient charge separation for solar cells. But this versatility comes with a great cost. Because if you look at the performance of these organic devices, they still lag behind the inorganic counterparts that we're competing with in key metrics like power conversion efficiency, longevity. And part of the reason for that is there's such a vast parameter space to explore in organic chemistry. We just don't know where to go. Part of the role of my group in this broader venture is trying to pin down what are some important structural design rules that we can put together to help us optimize the efficiency of particular processes. But as I've been working on this problem for the last decade and a half, I've come to realize sometimes we're trying to fight the wrong battle. Maybe we're fighting a losing battle, because there are certain things that come with these properties that we cannot avoid that are going to make organics worse in some basic regards. We have to learn how to live with them. So there are two of these I want to highlight that are really important for the work that I'm going to present today. The first is packing problems. So you can process organic semiconductors in this really nice, simple, cheap way at low temperature because they're very soft materials. Another part of them being very soft materials is they have a low dielectric constant. So any excited carriers in this material are going to strongly distort the lattice and feel their neighboring charge carriers. And kind of what this tells you is any excitation in organic material is going to be strongly localized, just one or two neighboring molecules. Why does that matter? Well, one of the most important things that any kind of device can do is move charge and energy around, whether it's a transistor, which is all about moving charges, LEDs, where you're injecting charges until they recombine, solar cells, where you produce charges and they have to get apart to the electrodes, you have to move energy and charge. But when you have this kind of regime, the only way you can move things around is with really very slow, cumbersome nearest or next nearest neighbor hopping. So this has been known for a long time, and because we can diagnose the problem, we kind of know how to deal with it. If you need to transport through nearest neighbor hopping, the best thing you can do is radically increase the coupling between nearest neighbors. So people have come up with motifs to have these very strong one-dimensional stacks or two-dimensional stacks, these three-directional couplings. So there are lots of packing regimes where you can maximize the number of strongly coupled neighbors between molecules to kind of boost the integrals that govern this transport. So you may be problem solved. But while this works really nicely on a sheet of paper and in your leading studies where they demonstrate this single crystal has very good transport, if you want to make an organic semiconductor device using the advantages of solution processability, it's never going to look like this. A real organic film looks much more like this. You get this horrible mess of different domains. You might have some of these well-defined crystalline domains inside where you know the packing, but they're swimming in a sea of amorphous material, maybe connected by some semi-crystalline regions. So you have to understand and work with not only these well-defined crystalline regions, but also the boundaries in between them. And these grain boundaries, the defects, turn out to have a huge impact on the performance of organic materials in the solid state. And this isn't just going to apply to charge transport. This regime is a useful reminder that the molecules that we put in an organic film, they have a very wide range of environments. So this is going to affect not just how they couple to their neighbors, but their energetic structure, the vibrations that they have, the things that they can do. So we have this terrible disorder that we cannot get away from because the materials are soft. And that's never going to change. The other thing that comes with working with molecular materials is their very unique electron-phonon coupling. And this is one of the defining characteristics of organic semiconductors. So we can have electronic excitations to generate these excited states, but these soft materials often also have a huge number of vibrational modes, localized phonons, if you will. And we can reconcile these motions with a really simple potential energy diagram, where you can photoexcite electronically and simultaneously excite certain numbers of quanta vibrational excitation. And we know what this looks like in practice. You get absorption and emission transitions that are just dressed by these additional packets of vibrational energy. Simple enough. And this does well to describe most of the basic steady-state spectra of organic materials, but it doesn't tell the whole story. Among other things, these vibrations, which are very soft and easy to activate, they are one of the main culprits that causes this carrier localization, the exciton localization on the previous slide. So they're deeply tied to this transport problem. They cause a lot of the broadening and disorder that we can't get away from. So they come with an important cost, but they also have a crucial advantage. As the community has started turning more powerful spectroscopies to the things that organic semiconductors do, we realized that these vibrations, they're often not just benign bystanders, they're actively involved in ultra-fast electronic dynamics. So we can see that there are many regimes where these vibrations cause different electronic states to mix together on these multi-dimensional potential energy surfaces. So we find electronic processes that are synchronized with or driven by nuclear motion. And what they can also do then, near these crossing points, is cause states to behave in entirely new ways. They can mix together electronic states with different character to give them totally new and unanticipated properties. So if we kind of draw back and think, well, what does this mean for a spectroscopist? These two problems, vibrations and disorder. At the end of the day, my job as a time-resolved spectroscopist is to tell a story about what happens in a material. So at its simplest, our job boils down to identifying a few key characters when we photoexcite, maybe singlet states, some triplets, maybe something exotic like this triplet pair. We identify their fingerprints, and we want to map them onto a simple diagram like this. And we can identify from the timescales of those fingerprints how quickly things relax, how quickly states convert from one to another. Maybe sometimes they're very fast and allowed, sometimes very slow and forbidden. When we map onto these diagrams, this carries with it certain assumptions that we need to be aware of. And this has been wildly successful for most of the history of organic photochemistry, organic semiconductors, but it has major limitations that come with these assumptions. So first of all, when we draw these pictures, we're assuming that the nuclei are frozen. So all of these states have a well-defined energy. The singlet is right here at this bar, the triplet is right here at this bar, and then there's some higher singlet and triplet levels up there. With that comes the idea that these electronic states are very well defined. They're pure. They have a unique character that we can pinpoint, and we know how singlets behave. And when we start from those two precepts, There are lots of rules that make understanding what goes on in these systems much easier, because there are rules that tell us what states can talk to each other and which ones can't. So the singlet and triplet probably can't talk to each other very easily because they have different spin. So that's a spin-forbidden transition. So if it happens, it should be really slow. The singlet manifold should be an allowed optical transition because they have the same spin multiplicity. Maybe this should be forbidden, very weak or non-existent. Exotic states like this, we could also say, well, they've got this weird multi-electron character, whatever TT means. That should also be forbidden because of things like symmetry. So we get this great simplification. No matter how many states there are, the rules tell us what should happen, and we just have to follow them. But when we factor in these ideas of disorder, when we factor in vibronic coupling, we see that these rules, they turn out to be just kind of suggestions or guidelines. And we're most interested in my lab in the places where these rules are broken, where states come close enough together in energy that vibrations and other perturbations totally rewrite the energetic landscape and give us totally new behaviors. And taking this concept, we can see, for instance, that states that should be totally dark, non-interacting with light, can actually very readily emit photons. States that should be static on the timescales that are relevant for organic solar cells can actually move remarkably long distances. So when we understand when the rules can be broken and find ways to control this, we can actually start to apply these materials in entirely new ways. That's kind of the principle behind most of the research we do. I'm going to illustrate how that comes out in two, possibly three stories that have been most fruitful in the last couple of years. And the first of these is on singlet fission. We're going to take dark states that shouldn't interact with light and light them up through careful molecular design. And this is within the realm of singlet fission. So singlet fission is a basic 2-for-1 deal in carrier multiplication or exciton multiplication that's unique to organic materials. You start with a photoexcited singlet state on one molecule. It can share its energy with another nearby ground state molecule. And somehow, through some quick hand waving, you can end up with 2 lower energy triplet states on separate molecules. So 1 exciton turns into 2. And normally, going from singlets to triplets is bad and slow because it's spin forbidden. So the magic of this process that lets it happen is this intermediate state that we call 1TT, the triplet pair state. At first, this was just kind of a mathematical construct. We realized about a decade ago that it's a real intermediate state we can see and touch and do things with. And roughly, you can conceptualize it as 2 triplets next to each other that are pointing in opposite directions. And because their spins cancel out, you go from a spin 0 state, the singlet, to this coupled triplet state where the spin is still 0, even though it's built of higher spin triplets. And then they separate on some longer time scale. So there's no change in spin in this process, which means as long as you conserve energy, it can be very fast and very efficient. And this has been studied on and off for about 60 years now. The most recent wave of singlet fission research was sparked by the idea that you could use it to make better solar cells. And in kind of the typical parlance of spectroscopy, we could say, well, we're starting in this bright singlet manifold. We're going into the dark triplet manifold. And it's harder to pin down what exactly this triplet pair state should be, but because it's made of 2 excited states, so it's got multiple excited electrons, and it's made of triplets, which are typically a bad thing, there are lots of reasons why this state itself should be dark. So why are we interested in singlet fission? To make better solar cells. And the basic reason comes down to the detail balance or Shockley-Queisser limit. So the idea of a solar cell is your material is going to be defined by a band gap. It transmits all photons below that band gap, absorbs all photons above that band gap. And in an ideal world, if you absorb a very high energy photon, you're going to collect a lot of energy out of the device, but that doesn't happen. The very first thing that happens in any solar cell material is your highly excited states from UV photons are going to relax down to whatever energy is defined by your band edge. So what happens then is you throw away all of this extra energy stored in those high energy photons as heat. So this thermalization loss sets up an optimization problem in single junction solar cells. You push the band gap too far to the red, then you're going to lose a lot more heat. If it's too far to the blue, you transmit too many photons. And that turns out to tell us the best you can do in a single junction solar cell is about 33%. Well, turns out you can beat that with singlet fission. And I like to point out, because there are really no new ideas. This was already pointed out by Dexter back in the 1970s, that if you slap a singlet fission material on top of a silicon solar cell, you could capture these high energy photons, generate a singlet in your blue material, and split that apart into two low energy triplets. And with clever engineering tricks, maybe both triplets can go into the silicon solar cell. And that allows you to recapture all of the gray area that's underneath the blue here as extra charge carriers, extra power conversion efficiency. So you're turning heat that would have been wasted back into energy. If you optimize this with the right pair of materials, you can boost the solar cell from 33% up to 43 or 46%, which would, of course, be transformative. The silicon PV industry invests billions of dollars to boost efficiencies by a fraction of a percent at this point. Like, we're very near the saturation limit. If you could get a cheap organic material that you can just spin or spray onto a solar cell, and it gives you even a fraction of this enhancement, it would totally transform renewable energy generation around the world, which was really exciting until it became illegal in the US. Fortunately, singlet fission also has some cool quantum implications, so we're allowed to do it. And this has been chased for a really long time, and it turns out to be an incredibly hard problem. I just want to highlight there's some fantastic work by Mark Balder's group at MIT. They're really driving the device implementations of singlet fission in the world. And this, I really need to update it. This is a paper that was published in Joule probably a year ago now. If you look at the external quantum efficiency of a reasonably good silicon solar cell, there's actually an enhancement in this region from the singlet fission material. So you're getting like 140% fission yield, transferring charges into the silicon and resulting in enhanced power conversion efficiency. So singlet fission solar cells are real. There is a real prospect that they can deliver on this promise, but it's a really hard problem. And I think this paper actually illustrates that point. The material Balder used here is silicon solar cell with tetrazine, which is the exact material that Dexter proposed in 1979. Now, in the ensuing 40 years, we have learned a hell of a lot more about singlet fission, about silicon solar cells, about organic semiconductor photophysics, about everything that goes into this problem. Surely we can do better. And this kind of illustrates what a tough materials problem this is. We still don't know all of the details that make singlet fission materials tick, that makes it hard to optimize them in a device setting. So what we do in my group is work on the earlier steps in this process to see if we can find better ways to make singlet fission occur, so that we can get away from materials like tetrazine, which are great for demonstrations, but are wildly impractical for applications. And some of this stems from a question I've been asking for about a decade now. How dark is a dark state? It's very easy for us as spectroscopists to say that state is dark, it's not going to absorb, it's not going to emit. But what does that actually mean? And looking in detail in a wide family of singlet fission materials, we found out, well, actually, this dark triplet pair state can be induced to emit photons pretty well, particularly at low temperature. You can get this unique redshifted emission in polyacenes, heteroacenes, carotenoids, and polyenes that are all characteristic of this triplet pair state directly emitting photons, not going back into the singlet. And we realize this happens through a symmetry-breaking vibronic coupling, similar to Hertzberg telecoupling. So this TT state couples to the singlet, borrows its intensity, you get a new mixed potential energy surface that allows it to emit. But this set up a really frustrating problem for me that was really crystallized when I started teaching my own graduate students. Because in spectroscopy, we learned, well, a photon doesn't give a damn what direction it's going in. So what goes up should come down and vice versa. So why is it that we can see the photon coming down in all of these materials, but we've never seen it go up? We've never seen the triplet pair state absorb. And to try and tackle that problem, I gathered together a zoo of pentasines. So pentasine is like the cheat code for singlet fission. If you put two pentasines on the opposite sides of this room, they will do singlet fission because there's just nothing else that pentasine wants to do. So we knew we didn't have to worry about that. But what we did then was we gathered together pentasines that can be coupled together, interact in all of the different ways that the field studies connecting pentasines. So we have these covalent dimers that are connected by a unique chromophore, a phenyl bridge, or no bridge at all. We have them in the 6,6' geometry and this 2,2' geometry. And then we have a family of thin films that pack into strong H aggregates, strong J aggregates, very weak J aggregates, and a system with no evident coupling between the pentascenes at all. All of them do singlet fission, but we wanted to go one question further. And we decided to try the most ridiculous simple experiment we could to see, well, does the triplet pair state absorb? We tried to excite it. So on the surface, this looks like a silly experiment to do. We're going to compare transient absorption spectroscopy, either pumping resonantly with this blue pulse or these blue arrows, versus subresonantly, something below the band gap where it doesn't really absorb, but where we think the triplet pair state might be. And the reason we thought this could possibly have a chance to work is because in a couple of our dimers, we saw very weak structure below the band gap that roughly lines up with where the triplet pair state should be. So we thought maybe there is a state down there, just very weakly absorbing. So what follows is a ton of pump probe spectroscopy, but the data maps onto a very simple interpretation. This is typical transient absorption spectroscopy on a normal singlet fission material. We have a signature of the singlet up here that decays, photoinduced absorption of the triplet pair down here that grows in. When we photoexcite with a 10 femtosecond pulse, we can see very smooth conversion between the singlet and the triplet pair. So this is typical singlet fission behavior in a strongly interacting pentacene system over a couple hundred femtoseconds. So now if we come in with our red pulse below the singlet absorption energy, we can see exactly the same triplet pair state signature that's present on longer time scales. But on the earliest times, there's no sign of this initial singlet decay. There's no sign that we started in the singlet state. The only thing we can see with 10 femtosecond resolution is the triplet pair. So we go from a regime with clear dynamics to a regime with no dynamics of conversion at all. Looks like we're directly photoexciting the TT state. We can use this same approach to study all of our dimers. These three show the same basic behavior. You pump in the blue resonantly. You have a distinct rise of the triplet pair signature, decay of singlet fingerprints. When you pump in the red, all you see is the triplet pair state on the earliest time scales that you can capture. But it doesn't always work. Oh, yes. It doesn't always work. In these two dimers, no matter where we photoexcite, we see the same behavior of singlet slowly-ish turning into triplet pairs from picosecond to many picoseconds time scale. Same thing applies in films. Most of our films, these M1 through M4, they show that when we pump in the blue, we get singlet turning into triplet pair with the very clearly identifiable time scale. Pump in the red, and the only thing we can see is the triplet pair state. But this film, this M5 with very bulky side groups, no matter where we photoexcite, we always get singlets and they slow and turn into triplet pairs on their own chosen time scale. So it looks like we're directly photoexciting this state, but we have to be careful. I've spent a long time at the beginning telling you these organic thin films, they're full of disorder and defect sites. So what if we're just pumping some weird defect state? And that's a really hard, really nasty question to ask. Fortunately for us, singlet fission gives us a way to at least infer the answer, because forming this triplet pair state isn't the end of the fission process, it's only the beginning. Once the triplet pair is formed, they can hop apart, they can undergo various spin evolutions, they recombine, they can evolve into these high spin quintet pair states and the like. And all of these things are deeply tied to the ability of the triplet to move, which is tied to nearest neighbor couplings. So if the local environment of your triplet pair state is unique, you're going to have distinct triplet pair or triplet transport dynamics. So you're going to see that in the subsequent evolution of the pair state. But when we look at our films, we see that their spectral fingerprint and their dynamics are identical across the entire evolution that we can capture of this pair state, which tells us that, no matter how we photoexcite it, it is evolving in exactly the same way, whether it's separating into long-lived triplets like in this film, or rapidly recombining because they're stuck in traps like this film. This sub-gap absorption that we're pumping is truly representative of what the material does. It's not just a defect. So that's great. We can go back with the understanding we really are pumping this triplet pair state now and think about what the different molecules are telling us. Because one of the most exciting things for us was that it didn't happen all the time, because that means there is some materials design principle behind it. And very crudely, we can look through and see, well, the ones that enable this direct excitation of the triplet pair, they're the ones that have the larger shift between uncoupled isolated molecule and thin film or dimer. So there's the largest intermolecular coupling between the pentascenes. So that tells us there's maybe some role for delocalization of this initially excited state. We can go further and look at the information that we often throw away as spectroscopists, the details of the spectral fingerprints. Typically, once we identify this is the fingerprint of the triplet pair state, this is the singlet, that just lets us extract the dynamics of these different characters. But these excited state absorption spectra carry a wealth of information about the nature and the properties of the state we're looking at. And the key for us here is that in all of the systems that let us directly excite this pair state, the triplet pair signatures carry these unique peaks in the near infrared, or unique solvent sensitivity in the visible that tell us there's a very strong character of charge transfer states, or in fact, charge resonance states in the wave function. Effectively, a major part of the wave function, whenever we're able to directly excite the state, is this charge resonance character, which is an electron transferring from A to B at the same time as it transfers from B to A. So it's a symmetric, non-polar CT type of state. And this is really the glue that holds it together. When there is no CT or charge resonance state, we can't excite the triplet pair. And this was great because we did have a problem with this observation, which, the whole point of singlet fission, at least nominally, is to make solar cells better. And the reason that this was able to be, a fundamentally new discovery in singlet fission photophysics 60 years after it was first discovered, we'll see we can directly excite it, is because it came from what seemed like a silly experiment. As spectroscopists, we don't usually pump a material where it doesn't seem to absorb light. But sometimes it's worth doing the silly experiments. But to kind of go to the next step for the application space, you don't want to use this phenomenon in your solar cell, because the solar cell needs to absorb the light if it's going to do anything with it. And this is such a weak absorption that you don't see it in the steady state. So this mechanism told us something about the nature of the triplet pair state. It's not just two triplets. Its wave function is much more complex. It has this charge transfer or charge resonance character, and that mixes with singlet character to give us this very slight ability to absorb light. But you're not going to put it on your rooftop. However, this gives us a design principle. So we sat down with our synthetic collaborator and we thought, is there some way that we can really ramp up this effect? And the very crude idea from the spectroscopy side was, why don't we just crank up the charge resonance coupling as much as possible? For us, that means smoosh the molecules together so the orbitals overlap more. So we had this idea, let's pin the pentascenes together with these very strong hydrogen bonding units, hold them really tight, and see what happens. See if we can ramp up this orbital overlap and change the photophysics. So Satish and his group, they made a family of these units are called Hamilton receptors, or HR pentascenes, as a monomer, dimer, trimer along this axis. So we could see what this charge resonance coupling is going to do. Now, if any of you know anything about supramolecular chemistry, you will recognize this was a woefully naive idea. Because as soon as you put multiple recognition units on a molecule for self-assembly, you open a whole can of worms. There are so many ways that these pentascenes can now couple to each other. So depending on processing conditions, we can get these beautiful micron-length nanoribbons or these more amorphous agglomerates. We can get very different kinds of coupling between them, H-type, amorphous, maybe J-type. At very high concentrations, we discovered a cooperative self-assembly mechanism where the pentascenes first form these hydrogen-bonded two-dimensional sheets, and then the sheets pi stack to form these beautiful, well-defined J aggregates, which have never been seen in pentascenes before. So we have this whole zoo of ways that the pentascenes can now couple together for us to explore. But the terrible news was every single one of these motifs that we studied, it does the same thing, which is what pentacene always does. It's going to fizz, but it does it in the normal way. And every one of these aggregate types, we start in the singlet state, and that decays to form triplet pairs in a typical pentacene timescale of femtoseconds to picosecond. So we found some really cool structures, found ways to engineer the packing of pentacenes, but it didn't give us what we wanted. But fortunately, my postdoc was undaunted and found one more trick up his sleeve, which was to induce an aggregation with anti-solvents. In this case, it turns out that these molecules really hate chlorobenzene, and that makes them pack together like nothing else. So when we dissolve these molecules in chlorobenzene, we get this absolutely gigantic shift in the steady state absorption, 350 millielectron volts. And this is totally reversible. If we put good solvent back in, it hops right back to this unaggregated free molecule position. But this degree of shift is by far the strongest interaction between pentacenes that has ever been reported anywhere. So this is really a gigantic coupling that we're turning on in the monomer and in this dimer. And now, when we look at the transient absorption spectroscopy, we see what we've been looking for all along. No matter where we photoexcite in these aggregates, the only thing we see is this triplet pair state, down again to the couple of tens of femtoseconds that are defined by our instrument resolution. There's an initial decoherence or dimming of this state, which should be dark, but is clearly bright because it defines the UV-Vis absorption spectrum. But basically what we've been able to do by ramping up these charge transfer couplings is turn this nominally dark triplet pair state into the primary photoexcitation of the system. So one photon is now actually exciting two electrons, two excitonic states simultaneously. So what this story tells us is that we can go from a kind of proof of concept observation where we can observe some systematic phenomenon, even if it's very weak, very small. And by understanding the mechanistic principle behind it, this charge resonance coupling, we get a design principle where we can rewrite the light matter interactions of these pentacene molecules and go from a forbidden triplet pair state to one where the triplet pair is the primary photoexcitation, or turn dark states bright. So now I'm going to change gears and talk about work we've done to go in the opposite direction, which is to take bright states and turn them off. And we do this with strong light matter coupling or polariton-enhanced energy transfer. So polaritons are a manifestation of strong light matter coupling. I'm just going to quickly define my terms. So the light that we use in my group are going to be these well-defined photonic states inside a Fabry-Perot optical cavity. So two mirrors separated by roughly the wavelength of light. If you look at this structure from the outside, it'll be highly reflective because it's made of mirrors until you approach this resonance wavelength that corresponds to one of these modes, at which point you can couple photons quite efficiently in and they'll bounce around for a while before leaking out one way or another. So with these structures, we get a well-defined photonic state in space because it's only between the mirrors and an energy defined by this resonance condition. And we want to make this light interact with matter. In my lab, we're interested in the electronic absorption transitions of organic semiconductors and dyes mostly. But the physics of strong light matter coupling don't really care about what kind of matter you use as long as the matter transition is well defined. And even the idea of a well-defined transition turns out to be very ill-defined in the field. And if you try hard enough, almost anything can go into the strong coupling regime. But what we're going to do is we're going to put our exciton materials inside of this cavity. And when we do, you can conceptualize what happens with this kind of video. So you couple a photon into the cavity, it'll bounce around for a while, eventually get absorbed, generating an exciton. If that exciton is well behaved, it will radiatively recombine, regenerate a photon that bounces around a bit more before it gets reabsorbed and re-emitted, reabsorbed, re-emitted. And you get this back and forth transfer of energy between photonic and excitonic states. Now, if that happens fast enough, which is equivalent to saying if these two things couple strongly enough, you can no longer tell, is it a photon or is it an exciton? And you have to talk about them as a superposition of the two, which we call a polariton. So it's a state that's simultaneously a little bit light and a little bit matter, which turns out to be very easy to describe mathematically. You can write down a simple 2x2 Hamiltonian that tells you this story. Very hard to work out what the hell this actually means in practice. And that's where my group is active. It's also useful from a chemical perspective, or at least it's popular, I should say, from a chemical perspective, to think about these states the same way we talk about molecular orbitals forming from atomic orbitals. We have two states, nearly resonant with each other, able to couple together. So they will inevitably hybridize to give us new product states, these molecular orbitals, the bonding equivalent of the lower polariton, the anti-bonding equivalent of the upper polariton, that mix the properties of the two parent states somehow, with the energetic separation between them governed by the strength of the coupling between exciton and photon. And what is the coupling between an exciton and a photon? Well, that's just the absorption strength. So it turns out you can control the strength of this interaction just by packing more and more molecules into your film to interact with this cavity mode, because the interaction is collected across all of the molecules that overlap with the mode, not just a single one, which is pretty cool. It gives us this laughably simple way to change the energies at which organic materials absorb and emit light. Instead of having some poor graduate student add another phenyl ring or a thiophene or God knows what else and do 6 months of purification and then their collaborator drops it on the floor, you can just put your molecules into a cavity and shift the energies at will. Sounds nice, but there's an important catch. Because these states are collective, they are accompanied by this sea of dark states that sit at the original exciton energy. So basically, if you have n molecules interacting with a photon, and there's one photon, there are going to be two bright states in the system, your upper and lower polariton. The remaining n-1 states should have zero interaction with this photonic mode. They're going to stay at the original unperturbed exciton energy. And because there's so many of them, they're probably going to dominate the cavity photophysics. So that might turn into a big problem for anything you want to do with polaritons, if you're not careful about it. But people have been studying these for a long time, and roughly a decade ago, the community started to realize you can find all sorts of weird and wonderful effects when you put molecular systems into the strong coupling regime. So you can greatly enhance the rate and range of energy and charge carrier transport. You can change the physics of donor receptor decay and charge transfer, things that are relevant to organic solar cells, alter the work function. And this is all just by putting your materials between a pair of mirrors. What's really taken the field by storm in the last few years was the recognition if you form these polaritons by coupling to the infrared absorption bands of certain bonds, you can alter the rate and selectivity of certain thermally activated chemical reactions. Again, just by running the reaction between a pair of mirrors. Pretty wild. And this has created this massive hype about the idea of polaritonic chemistry, where you can use polaritons or strong coupling, some kind of selective catalyst to steer reactions and maybe steer photophysics in new directions. But the dirty secret in the field is that while we as a community are very good at slapping a new material between a pair of mirrors and seeing something different has happened, we're terrible at understanding why that is. So almost all of these results that I've shown, the community has no consensus about why it happened, how we can harness this in a new reaction or a new material. So without design principles, all of this is just hypothetical still. So what we're trying to do in my lab is understand what's going on in these kinds of reactions so that we can start to really harness polaritons or realize where everybody has been going wrong. And kind of lurking in the background, I'm not going to talk about this in detail, but it underpins a lot of our interpretation. The community likes to talk about the polaritons because they're really sexy states. They're these gigantic coherent excitations involving millions of molecules that are kind of synchronously coupled to the photon. They have lots of interesting properties like long-range transport, but they are not alone, and they are by far the minority in the cavity. They're swimming in a sea of dark states, and we have to understand the dark states to understand cavities. And this is known in many areas. For instance, polariton condensation is one of the coolest things that polaritons do, but you can only understand condensation by starting your system in a bunch of dark states that scatter into the lower polariton. But the interplay between polaritons and dark states also impacts the long-range transport that we and others have observed, and it ruins most spectroscopy experiments that we can do because they give rise to a whole sea of artifacts. And it gets even worse because the states aren't just dark. As soon as you look at real materials, they're not these perfectly well-defined exciton energies that define that model on the previous slide. they are broad disordered potatoes. And as soon as you have disorder, this idea of bright and dark states starts to fall apart, and everything becomes a little bit gray. There's a smattering of photon character in every state, and the brighter states aren't quite as bright as you would. So all of this is lurking in the background in everything we think about polaritons. I'm just going to quickly take you through a model system where we can start to see some real design principles for how to use polaritons productively. And we wanted to start with the most reproducible and best understood interesting concept in polaritons, which is long-range energy transfer. So it's been known for a long time, if you put a donor and acceptor molecule into the same cavity, they can simultaneously hybridize with the photon to form this ladder of polariton states, a lower polariton, which is mostly acceptor-like, an upper polariton, which is mostly donor-like, and a middle polariton, which strongly mixes the wave functions of the two. And what's been seen is that no matter where you photoexcite in the system, you're going to see lower polariton emission. So if you think about this as exciting a donor and then capturing acceptor emission, this allows you to get donor-acceptor transfer. Quite remarkably, this concept works even if the donor and acceptor molecular layers are separated by as many as 2 microns, way beyond Fret's wildest dreams. So this is really long-range coupling or interaction between the molecules mediated by the cavity. But it's also kind of cheating, because this is not a donor state, this is not an acceptor state. All of these states are mixed together. So it's really a new quantum system. And then when you think of it this way, in the cavity, when you photoexcite an upper polariton, you're just getting relaxation down this polariton manifold. And it eventually leaks out of the bottom state. But the bigger challenge is, while this has been seen many times, this is a really hard system to set up, because you have to carefully balance the donor-acceptor strengths, the relative energies. There are basically no knobs you can turn. And we like to turn knobs in my lab. So we wanted to step back and think, could we get this same behavior when the acceptor is not in the strong coupling regime? Basically, can the polariton just be quenched by an acceptor that is not itself strongly coupled to the cavity field? Because if it can, we can start to use all sorts of tricks of chemical analysis to understand properties of the polariton. And this took a remarkably long time to set up, because it's very hard to find the right pair of materials. We eventually settled on this very poor donor-acceptor pair, rhodamine 6G donor, copper phthalocyanine acceptor, which have pretty poor spectral overlap. These are spin-coated in a polystyrene matrix. And the nature of this system is then we can independently tune the concentrations of the species. So rhodamine is going to form polaritons. We can tune its concentration to change the Rabi splitting. The copper phthalocyanine acceptor, we can change its concentration to tune the donor-acceptor distance, which is going to kind of cover the baseline energy transfer properties. And we can tune the length of our cavities with this wedge structure to sweep the polariton energy across the acceptor absorption band. So the first thing to check is, do these things transfer energy at all? Polaritons are made of photons, so they want to emit light. So the easiest way to check, are they being quenched, is to check the polariton emission. If we look at our thin films, as we increase the concentration of acceptor for this 33% donor loading, the rhodamine yield progressively decreases, as typical for a poor Fret pair. When we put it into the cavity, we see exactly the same behavior. Strong polariton emission when there's basically no acceptor, highly quenched when there's a lot of acceptor. And if you look closely, you can see, well, this degree of quenching is larger in the cavity than it is in the film. And this is the first sign that it's not just the dark states inside of the cavity that are transferring energy, because that should happen, but there's something more going on when we put it in the strong coupling regime. So then my poor students had to start a systematic study where we started turning all of the knobs we had. So the plots I'm going to show come from analysis of probably it's over 200 cavities now, systematically tuning various design parameters so we could get real trends on what is governing this quenching. So what did we see? If we look at the energy of the polariton mode, so these are going to be plotted as Stern-Fulmer analysis, where we're looking at the intensity of light emission relative to the unquenched case. A steeper slope means more efficient quenching. So as we increase the spectral overlap between polariton and acceptor, it gets quenched more. And that's what you would expect for a Fret process. It is maybe just getting absorbed by the quencher more because it's more resonant with it. But if we sit at one particular spectral overlap position around 650 nanometers and just increase the rhodamine concentration, so the collective light matter coupling strength, we see that for very weak coupling, it's barely better than the bare films. But as we ramp up the collective light matter interaction, it gets more and more efficient. So this is a process that is actually sensitive to the collective interaction of all of the molecules with light, which tells us it's something polaritonic, which was kind of exciting, but also really disappointing. Because if you're used to looking, if you're used to looking at these kind of plots, you realize we're changing the slope by like a factor of 3, which is incredibly underwhelming for this collective excitation that should span hundreds of thousands or millions of molecules. Surely its Fret radius should be more than 50% larger than the bare film. What's going on? Fortunately, Rana recognized if the polariton is able to do something, it's doing it against a very fast clock, because as soon as the polariton forms, it wants to decay as a photon almost immediately, because these are very lossy cavities. They've got 10 femtoseconds to do something. So maybe it is remarkable, but we need time-resolved experiments to understand. So very quickly, we did a lot of transient absorption in our films and cavities. What I'm going to plot is increasing acceptor concentration from left to right. And as we increase the concentration in films, we see the rhodamine signatures decay faster. We start to see acceptor signatures turn on. So basic donor-acceptor transfer. And now we can put them into cavities, which look really jazzy. But this is just because of weird optical effects that happen when you photoexcite a cavity. These are well known as artifacts, but we can read them because the nature of the artifact depends on where the photoexcitation sits. It looks like this derivative when the excitation sits on rhodamine, and the derivative actually flips over when it goes onto the copper thallocyanine. So again, we can map this as donor transfer to acceptor. It doesn't look like much in this cavity, but as we move our cavity mode redder and redder, the effect gets stronger and stronger until it looks like we're depleting the rhodamine donor in under a picosecond, compared to hundreds of picoseconds for the bare film. So we were wildly excited until we remembered the golden rule of polaritons, which is that they're always going to break your heart, because there are so many artifacts in these things. You have to be incredibly careful in how you decompose it. It took us a long time to work out the right robust method. When we did, we found out there are very, very tiny differences at most between the different cavities, but a massive difference between polaritons and the film system. And that was enough to build a simple kinetic model. I'm just going to go over the key points. With this model, we can put together all of the processes that happen in our films, whether it's relaxation of the dark states or the bare excitons, direct transfer to the acceptor, and then there's equilibrium between dark states and polariton communicating with the acceptor. And I'm happy to talk about these more, just to say we can benchmark all of these rates very carefully from our reference experiments with low acceptor or cavity 3, which sets up some really fundamental constraints that require basically these processes, the back transfer, the lower polariton decay, and the polaritonic energy transfer all have to be competitive with each other, which sets up a really strong constraint on the photophysics of the system and leads to some wildly uncomfortable numbers, which I'm just going to leave you to ponder. Basically, the back transfer from polaritons back to the dark states has to be in the attosecond regime. The polaritonic enhanced energy transfer can be no slower than a femtosecond to describe our observations, which means that strong coupling is actually enhancing this donor-acceptor transfer by a factor of about 100,000, which starts to be consistent with this very big collective state. It's just there's a faster process of scattering back to the dark states that slows it down. And this tells us the way to improve what polaritons do is to manage this equilibrium. But there is real scope to use polaritons to redirect photophysics. So with that, I'm just going to jump to the kind of overview slide to point out what we want to do as spectroscopists is always draw a simple picture of photophysics where we can map onto really discrete states. But we have to be humble and realize quantum mechanics doesn't give a damn about a convenient picture. It's always going to do these things it's going to do. There's always going to be disorder, strong vibronic coupling, But once we embrace that, we can start to realize new ways to change the photophysics of organic materials and apply them in new ways. Whether we mix photons into our electronic states to create these hybrid polaritons, or we squeeze molecules together to introduce new intermolecular couplings and redefine what are the absorbing states. When we embrace the complexity of these organic systems, we find entirely new opportunities to apply their photophysics. So with that, I'll just thank my amazing group again, and I'd be happy to take any questions.